to you. Okay. So no logistics stuff today, so I'm going to go ahead and go right into the content. We basically finished everything for capacitors last class. We did a bunch of example problems. We talked about dielectrics at the end. Alright, just need everyone to settle down. Alright, need everyone to settle down just so everyone can hear me. So if you're still talking, I'm going to wait till everyone finishes talking until I start talking. Cool, perfect. Alright, so talked about dielectrics. So today, basically, I'm just going to do a couple example problems with it, show you all how I would work through, again, just showing you what some example problems look like and then how I would actually go about solving them. And then we're going to go ahead and move into resistivity, which leads us into resistors. So we'll see how far we can get. But that's the plan for today. So, to immediately start off with, I have a problem which is going to be either the same one or resistance. And so the question says, what voltage is applied to a 5 microfarad capacitor of a heart defibrillator that stores 36 joules of energy? That's part A. So remember the problem solving process that kind of is helpful is write down what you know. So knowns and unknowns. So for part A, knowns. We know capacitance equals 5 e to the minus 6 farads. And actually I'll just write the whole 5 microfarads, which equals 5 e to the minus 6 farads. And we know that it stores, that this is a capacitor which is storing 36 joules of energy. Okay, so the next, and then we are trying to, the unknown is voltage. Voltage equals who knows what. Okay, so this is where you then have to just remember, okay, we know the energy in the capacitor, we know its capacitance, we're trying to find voltage. Is there a expression that relates these things together? There is. So you would then look at your formula sheet. And this is where you would need to remember that the energy stored in a capacitor, I say need to remember, or it's on your formula sheet, is 1/2 Q times V. We had a bunch of different versions of it. So 1/2 Q times V, but using C equals Q over V, you can get a bunch of different expressions. So if you use that one, you can say Q equals C over V. Or sorry, Q equals C times V, so 1/2 CV squared. And then the last one is you plug in for voltage. And voltage is going to equal Q over C. So 1/2 Q squared over C. Those are the three expressions for it, which if you can remember the first one, 1/2 Q times V, and you can remember C equals Q over V, that's just what I did, is I derived the other two by just plugging in things. Or you can just have all these written down. I probably recommend having them all written down. So great, we have an expressions, and all we have to do is see if we have two knowns and a third unknown. So we look at these, we say, do we know Q? No, we're not going to use that one. Second one, do we know C? Yes. Do we know U? Yes. So we can solve for V. There you go. If you only have one unknown in an equation, you can solve for it. So we will use this one. So U equals 1/2 CV squared. We're solving for V, so V is going to equal, I guess V squared, I'll do more steps, 2U over C, so V equals the square root of 2U over C, and you just plug in the numbers, so 2 times 36 divided by 5 e to the minus 6. There you go. And that gives you a number. So, plug that in. I'll plug it in my calculator. You can plug it in. Well, I say I can plug it in my calculator. My calculator is dead. So I'll use a different one. Pro tip, when you go into the exam and we have that, make certain your calculator works. Otherwise life will be challenging. 2 times 36 divided by 5, where is it? 5e to the minus 6. All right. So I get, oh, yep, yeah, great. What voltage? Okay, I was a little concerned there. 3.8 kilovolts. There you go. Everyone else get that? Anyone get anything different? Cool. There you go. So that's how you're going to solve one of these problems. The thought process being, you know it's a capacitor, go to the equations that relate capacitors. Then you just, if you ever see energy with a capacitor, you should immediately go to this equations for energy stored in a capacitor. My reminder to you is please do not use the energy as a capacitor as just Q times V. That is the energy for a point charge. Energy on a capacitor is 1/2 Q times V. We went through the derivation last class. Please don't make that mistake. Super easy mistake to make because you'll see energy, you'll see Q, you'll see V, and you'll be like, this is, I'll use either one of these, and you may use the wrong one. Make certain you use the one for a capacitor because it's the one we derived because it's a bunch of point charges. Yeah. You got something different. All right. Anyone else get something different? Again, I'm using a different calculator, so it's very likely I could have messed it up. I got 3,794.7, which then 3.8. I just rounded to 3.8 kilovolts. Is that roughly what you got? All right. I'll check on that later, but this should all be good. Let me double check the math. 1/2 C times V squared, so you multiply 2 over, yep. Okay, awesome. Now again, as I mentioned to you all, it is very likely as I'm solving these that I could make some math error. That is why I have you all also checking the math and double checking it. If this was an actual test, I would double check my own work. In this case, I don't necessarily have the time to do that, but I have 200 of you to double check my work. So I will leverage that. Okay, part B. And my goal is not to make mistakes, but this is just part of the, I just want to continue to emphasize to you all, making mistakes is normal, that's okay, but do everything you can to not make them, and when you do make a mistake, learn from it. Sometimes you can feel really bad when you make a mistake, you'll be like, that's stupid, how did I make that error? Trust me, a billion people before you have made that same error. That's part of life. It's okay. All right, next one, we are trying to solve for Q. So now our unknown is Q. I have the knowns on the last one. Q equals who knows what. And so at this point, we found voltage, we have capacitance, we have energy. So you can use any one of these equations to solve for it. Just pick the ones that have Q in it, either the first one or the last one. I'm going to pick the first one because it doesn't have a squared. So that makes my life a little bit easier. So I'll just use U equals 1/2 Q times V. We just found V, so great. So 36 joules equals 1/2 Q times 3.8 kilovolts. So if we wanted to use the exact value, it's off my calculator, so I'm going to use 3.8 kilovolts. 3.8 e to the 3 volts. So therefore Q equals 2 times 36 divided by 3.8 e to the 3. Two times 36 divided by 3.8 e to the 3. And I use e times 10 to the 3. So you get 0.0189 coulombs. Well, again, you have to be, this is another thing you have to be careful with. Coulombs is the unit of charge, whereas C is the variable we use for capacitance. It's unfortunate that they're the same thing, but please don't mix this up when you're doing problems. Coulombs, whereas the previous C was capacitance, was a variable for capacitance, not the unit. The unit for capacitance is farads. So, alternatively, 1.89 e to the minus 2 coulombs. Same thing. All right. Any questions on this problem? Okay. Fairly straightforward. Basically just plug it and chug it into the right equation. The only trick is just making certain you have the right equation. It's a one-step problem. Some of these problems you have to find something, then find something else. This is one step. You have the equation, you plug it in. These are the easiest ones to solve. On the test, I'll basically be giving you some one-step problems like this, and some problems that are maybe 2 steps or 3 steps, where it's not just plug into one equation and be done with it. You may need to relate 2 equations. And so make certain you're comfortable doing both kinds. If you're comfortable doing a 2-step problem, you're going to be comfortable doing a 1-step problem. Okay, next problem is how much surface area is necessary in order to make a capacitor with a capacitance of 1 farad, assuming we have a gap of 10 micrometers and that we are able to maintain a vacuum in the space between the plates. Then the follow-up is how much surface area is necessary if we add a dielectric. Hopefully my computer unfreezes at some point. If not, I'll do it on the blackboard. Hooray, I don't have to do it on the blackboard. All right. So, same thing, knowns and unknowns. Knowns, we know that capacitance equals 1 farad. We know that the distance, and you know what, I'm going to draw a picture for this because it just again helps us visualize what the variables represent. So there's one plate of my capacitor, there's my other plate of my capacitor. So this is the distance between them, and then it has some capacitance, and it also has some charge. And this is the area. Area. Okay. So we draw on pretty much most of the relevant things. So there's some C, there's some Q, there's some V. I guess there's some energy, but we don't need to worry about that. So our knowns, C equals 1 farad, and D, so this is a gap. This is translating what the word problem is saying. Assuming we have a gap of 10 micrometers, this gap is denoting the distance between the plates, so that's the variable D. 10 micrometers, which equals 10 times 10 to the minus 6 meters. And our unknown is the area. All right. So, with this problem, that what you're going to want to jump to is remembering that capacitance is a geometric thing, and that it is dependent upon the distance, the area, and then what's in between them. Since it's vacuum, it's just epsilon naught. So because of that, so let me make a new slide. I need more room, so I'm making a new slide. This is where, again, it's kind of like the last one. This is a 1-step problem where you can basically just be like, do I have any equations that have all these variables on them? Turns out we do. So our life is simple. All right. So then we know, we look at our formula sheet that we'll conveniently have during the test. I say formula sheet you conveniently have, the one that you all make. Area over distance. And so we look at this and be like, do we have everything we need? Well, we know epsilon naught, we know A, we know D. And in fact, just to keep it general, just to prepare for the next one, I'm going to put kappa here. Because if you'll remember, at some point we're going to have to include a dielectric in this problem. That's step B. So I'm going to include the general expression for now. And then you just remember when it carried, but then once we start talking about dielectrics, we needed to bring it in here. So it's one piece at a time. So kappa equals 1. Kappa is this thing, dielectric constant. Dielectric constant. So now it's just plugging and chugging. So, and I'm going to solve for A first. I prefer to keep things in terms of variables as long as I can. Just makes it easier to work with and easier to track. But you do whatever you prefer. I recommend keeping things in terms of variables when doing problems. It lets you cancel out stuff sometimes. And again, it's just easier to track. Once you put in the numbers, it's hard to remember what the numbers actually are representing unless you keep the units in there. So it's just a good problem-solving strategy. So 1 divided by 1 times 8.854 e to the minus 12. All I did was plug in the values for all these variables, and we get a number. 10 e to the minus 6 times 1 divided by 8.854 e to the minus 12. All right. You get a real big area. You get 1.129 e to the 6. meters squared. And you may be like, that's really big. And you would be correct. And this is where I was saying before, when you have a capacitance of 1 farad, that is a very strong, that's a large value for capacitance. I'll tell you, you can make a 1 farad capacitor without needing this big of a surface area. Then the question is, how do you do that? Well, one way is if you make the distance smaller, then the area doesn't need to be as big. So that's one way to make a 1 farad capacitor without needing to make it ginormous. Just make the distance between the plates smaller. You may think that a micrometer is a very short distance. It is a small distance, but we can get much smaller than that with today's technology. The transistors in your phones are in the order of nanometers, which is 10 to the minus 9. Granted, you're not going to want to make a capacitor with nanometer stuff because you're going to run into other problems there. But all that to say, we can get real small. All right. The other way, I'm going to use the exact same question. So to refer back to the problem, it said, how much surface area do I need if I add a dielectric with a dielectric constant of 5? It doesn't have any units, it's just 5. Dielectric constants don't have any units. So it's the exact same problem, but now, so we set up exactly the same way, but now kappa equals 5. And if you wanted to, you could go through all the math. It's going to be the exact same math. Or you can just recognize that if I multiply this by 5, I'm going to get 1/5 the area. So that's a real quick way of doing it. Sure, you could brute force it. I could literally set it up exactly the same way. A equals D times C over kappa epsilon naught. And just you see here I'm dividing by 5. So my area 2 equals 1/5 area 1. And this is area 1. So this is the quick way of doing it. If you want to do out the math to prove it, go for it. But it's literally the same number here, the same number here, the same number here. There's a 5 in the denominator, so I'm just dividing by 5. And that is much easier to plug into a calculator. 1.129 e to the 6 divided by 5. And now I have made it 2.25 e to the 5 meters squared. Still really big, but you can get much bigger dielectric constants than 5. So there you go. That's the solution to this problem. Capacitor problems, there's not really much I can give you that's super complicated. I mean, at worst, I can maybe give you, like for instance, what would be a 2-step problem for this? A 2-step problem, maybe I combine these 2 problems together. So I say, find the energy stored in a capacitor that has 36 joules of energy, has an area of this and a distance of this, and it's in vacuum. In that case, you still know energy, but you no longer know capacitance. You have to find capacitance by using this equation, by using C equals epsilon naught over D, and then you plug that into the other one. 2 steps, because you had to solve for one equation and then use that to plug into the other equation. So that's an example where you would actually have to kind of, again, you can't just look at one equation and be like, oh, I have one equation that relates both energy, area, and distance to get me whatever I needed. You would need to use 2 equations, 2-step process. Make sure you're comfortable doing those because those are the ones that trip people up, because it is very, very easy to do a problem like this, where you just look in your formula sheet for the variables and you're done. It is much more difficult to be like, okay, I have to solve for one to find another, and that's just going to take practice for you to be comfortable with it. So, capacitors, though, the problems aren't too bad. If you've looked at the problem set, they're all kind of more the same. Yeah, if you're certainly having problems with this, please let me know. Any questions about capacitors? Because we are done with capacitors. But if anyone has any questions, I'm happy to field them now before we move on to something else. All right. So we're going to move on. The quiz this next week. So the quiz this Friday is potential and potential energy. The one on the 14th is capacitance and resistivity. So we need to finish up resistivity so you have all the content for it. But then basically after today you're going to be good to go for that quiz, which is even a week and a half from now. So resistivity, what is it? Resistivity is a new thing. So capacitance was how much charge you can store per voltage. Resistivity is the property of a material to resist the flow of electrons. What can I kind of compare this to? Can't really think of anything off the top of my head, but basically just like some materials it's easier for electrons to flow through, other materials it's harder for them to flow through. Think of wood. It's going to be hard to push electrons through wood, but it's really easy to push electrons through metal. So you see here, let's just pick any metal, and all of them have different ones, and this is a very complex thing to actually like theoretically calculate the resistivity, so I'm not giving you an equation to calculate the resistivity at room temperature, because all of these are more experimentally done. You can do them theoretically, but you're literally trying to figure out how easy or difficult it is for electrons to go through, and that's can get very complex. Again, I don't actually know how to do that. Not something I learned because of how much you have to know for it. But what we are going to talk about is that this property of a material changes with temperature. So again, we see here, we see the resistivities. We see that wood has a very high one. That means that it's very hard to push electrons through wood. That should be straightforward. We don't use wood in our circuits. Whereas silver, copper, and gold, these are 10 to the minus 8, the resistivity. So that is 20 orders of magnitude, or 19 orders of magnitude smaller than for wood. And silicon, you see here, that's around 0.1 to 2,300. You may be a bit confused by that because you've heard that the circuitry used in your phones has silicon in it. That's the semiconductor industry. That's because silicon is not actually what the wires in your phones are. It is used for something different. I'll talk about transistors eventually after we talk about resistance and stuff like that a bit more. But this is basically, it has a high one because silicon is actually a semiconductor. When you add stuff to it, you can either make it conducting or not conducting depending on other variables. So that's why it's really high, but it's still used in circuitry because it has unique values. And there's the rest of them. When you increase the temperature, we get this equation where if you have the resistivity at room temperature, I will give that to you on a test. If I ask you this, I will give you the resistivity and I will give you the temperature coefficient. But you'll put that here. You'll basically then just do 1 plus the temperature coefficient times the temperature it's at minus room temperature, which we just say is 20 degrees Celsius. And that gives you the new resistivity. The resistivity is changing with temperature. And this equation describes that. And that is a very common problem I'll ask you. I'll ask you, how does the resistivity at 40 degrees Celsius compare to at room temperature? And you just plug in values and figure that out. Alright, so that's the math behind it. Now, spend about a few minutes. Why do you think that matters? Just think in your brain. Why would increasing the temperature of something make it harder for electrons to go through it? Brainstorm. This is what physicists had to do back in the day when they were figuring this out. They're like, what's up with that? That's weird. Alright, let's hear some ideas. I'm just going to jot them all down. I'm not going to tell you whether they're right or not. We're just going to kind of write them down and then think through them. Yep?
Because particles move more when they're hotter.
Particles move more when they're harder. When they're hotter. Harder. Okay, so which ones are going to be moving more? You think the electrons or the atoms in the material? I heard someone say atoms, so I'm just going to write that down. Atoms of material moving faster. Atoms of material. Oh, goodness. Moving faster. Okay, saw someone else's hand up. Yep.
Because hotter materials are more likely to have their outer electron shells.
Okay. So hotter materials, more likely to have filled orbitals. Okay? The material expands. Okay, so thermal expansion. Yep.
Since there's more motion in atoms and electrons, then there's a higher probability of collision.
Okay. So higher probability of collision, and I'm going to draw an arrow to the first one. All right. Anyone else? All right. So these are all some ideas. I like that there's many different concepts used here. So yeah, so we're just going to kind of start from a fundamental thing of what is temperature, what does it mean for something to get hotter, and that's going to lead us to that first one. So these were the ideas. So, and then we'll go with just knowns. Temperature increase does mean that particles wiggle more. Yep. So that is accurate. As you increase the temperature of something, that's literally what it means. If something's hotter, that means that there's more thermal energy, which means just that atoms are wiggling a lot more. The material does expand. I will say that effect is going to be minor. Interestingly, though, a material expanding actually would decrease the resistance. And so it does actually have some effect, but it ends up decreasing a little bit for the same reason that if you increase a highway, if you increase the number of lanes on a highway, you have more space for cars to go. If you make a material bigger, if you have a fatter wire than a thinner one, you end up allowing more space for electrons to flow. So, yep, temperature increase does increase size, but this decreases resistivity. Rho is resistivity. And then we have the last one. Hotter materials more likely to have filled orbitals. Actually, as things get hotter, you're going to have more energy, so it's actually more likely for you to strip electrons away. So actually, in that case, you may introduce more electrons into the system, which actually won't have an effect, but that's a really good area to think about. I like that you brought in the filled orbitals there. So, the quick explanation of it, and you all actually got it down, which is awesome. This is kind of just a fun thought experiment. This is what it means to do physics, is you observe some phenomenon, and then you use what you previously known from what other people came up with to explain the thing. And that's exactly how we're going to do this. So we just went through those knowns. So we have here our atoms and our wire. And they go on forever. I'm not going to keep drawing them. As the temperature increases, they wiggle all over the place. And basically, yeah, as an electron is flowing through here, since they are wiggling more, they are kind of taking up more space. And so it's going to be less likely for the electron to be able to make it through it. It's going to bounce off more, and if it bounces off, it's probably going to get more energy in the wrong direction. And so it ends up, it makes it harder for it to go through because it is bouncing off of more things. So, as T increases, electron bounces off more. Therefore, rho increases because velocity of electron is going to decrease. If it's bouncing off, it's going the wrong way. And this is kind of the interesting thing about this is maybe you've thought about this, maybe you haven't. I hadn't thought about it before physics 2. What does it actually mean for an electron to go through a wire? Is going to be to the right, because that is the flow remember, it wants to go from higher to lower energy. So if you hook up to a battery, it's going to go net to the right, but it's going to end up bouncing off a bunch of times. But the net flow is all to the right. And the net velocity of this, I think I have it in a later slide. If not, I'll just mention it now. I want to check whether I have it or not. All right, I think I have it in resistance 1. The net velocity of this is like millimeters per second. It's real tiny. The drift velocity of an electron, drift velocity meaning that average velocity of them kind of going through the wire, is on the order of millimeters per second. And then you may be confused because you may be like, but why when I turn on the circuit does the light bulb turn on instantly? That's because there's electrons in the wire at all times. So the second you hook that up, there's electrons near the light, there's electrons in the filament of the light bulb which move instantaneously. They see that potential difference instantly and they start moving. It is not that the battery makes electrons which then have to flow all the way to the light bulb. All right. So there you go, that's the explanation. Heats up, more collisions, slower. Now to do some actual math with it. As I told you all this, not too many resistivity, there's not much we're actually going to do here. It's basically just going to be this one equation. Once we get to resistance we can do more, but for now we can't. So the question is, what temperature change is required to double gold's room temperature resistivity? I give you the temperature coefficient, I give you the resistivity at room temperature. I told you all I'd give this to you, and now it's just at what temperature change is required. So please do not give me final temperature, because that's not what I'm asking for. I'll tell you the answer here I have slightly off, but you're going to go and just round it. Round it to the closest one. The answer here I just realized is off by a few, it's off by 4. So if you get an answer, it's off by 4, find the one that's close enough to it by 4. Yeah.
Is that to the 8 or to the negative 8?
That is to the negative 8. No problem. Yeah, for pretty much all metals, they're all around to the minus 8. And for the sake of clarity, don't worry, I'm gonna put it back up there in a second. I'm gonna change all these by 4, so the right answer is actually the right answer. It's either I do it now or later. All right. So I've increased all the values by 4, so the right answer is now there. That gives you any peace. Alright, I'm going to give you all about 10, 15 more seconds. What's fun is you're going to find that the calculation for this is real quick. So it's all just figuring out how to do it appropriately. Alright, give you all 5 more seconds. So 5, 4, 3, 2, 1. Okay. So I gave you all the equations, I gave you all the variables. So you didn't even have to do the thought process for figuring out the right equations, but if you did, basically if it's resistivity, if I give you alpha, if I give you rho, and I'd say temperature, jump to this equation. That's the conceptual link you want to make in your mind. If I'm talking about resistivity and temperature, use that equation. So, here's how you do this problem really quick. You say that rho final is going to be 2 times rho naught. Rho is just that's resistivity. So therefore, if I plug this in, I get 2 rho naught equals rho naught 1 plus alpha. And I'm going to rewrite this as delta t, because that is t minus t naught, delta t. So that's what we're solving for. And look, you see here, oh, rho naught, those cancel. So I get 2 equals 1 plus alpha, delta t. Well, 2 minus 1 is 1. 1 equals alpha delta t. So it's just 1 over alpha equals delta t. So you get 1 divided by 0.0034 equals delta t equals 294. There you go. The really quick way to figure this out by just looking at the equation is, again, it's basically what number do I need to multiply rho naught by to double the temperature? Well, I need to this needs to be 2. Well, if it needs to be 2 and this is 1, that needs to be 1. So then it's just 1 divided by that gives me the temperature. That's just what I did in math. But you can conceptually kind of look at that and figure that out as well. Really comes out to a really easy thing. But these are good problems to do where instead of giving you values at the end, I say something's doubled. And you should, like, these are things that eventually you'll be able to hopefully do very quickly. There it is. And most of you all got this right. Fantastic. Okay. This is not where I want to be with that. Okay. I'm going to go ahead and move into resistance. I'm going to kind of skip Ohm's law right now, and I'm going to come back to it. So Ohm's law is here. We're going to spend more time on that in the next group of slides, but I need to bring up resistance here to be able to actually talk about its relationship to resistivity. So resistance is the thing that you're more often going to see, and that's what you're actually going to use. But the reason we need to care about resistivity is because the resistance of a wire is going to depend upon what kind of material you use. If you use gold, silver, copper, iron, whatever, that matters. And this expression gives us what that relationship. So what is resistance? Resistance is basically, given a voltage, how much current, and we're going to talk about current. Current's basically just how much charge moves through it per second through the surface area. So this is the more functional definition. Given some potential difference that I apply, remember potential difference is like a difference in heights. Once you put a charge there, it gets energy, it wants to go to lower energy. So if you have a difference in potential, you're going to have charges wanting to move from the higher energy to the lower energy. And so once you provide that, they're going to want to flow. That flow is going to be current. Current is that flow of, in our case, moving positive charges, which is opposite of what's actually happening, but that's the way we've defined things. And depending on what wires you have there, it's going to depend upon how much current you can get. So if I put a 5-volt battery to something with a very high resistance, you get a very low current. If I put a 5-volt battery to something with a very low resistance, you get a very high current. This is basically the idea of when you short something out, you provided a path with very low resistance, the current was super high, and it likely broke something. We'll spend more time on that, but I just really need to quickly cover that so we actually understand what resistance is. And now that we have resistance, we see here that it is the resistivity times the length of the wire over the area of the wire. And the area is the cross-sectional area. So in this picture here, the area is that side there, or just any cross-section through it. And so current is flowing in some direction. We'll just say it's flowing this way. It doesn't really matter what direction. And the cross-sectional area is that perpendicular, the area that is parallel to that, the area vector which is parallel. And hopefully this equation makes sense. As I increase the length of the wire, I literally have to push electrons through more stuff. There's going to be more collisions happening. I'm going to be losing more, so current is going to be decreased. It's going to be harder to push it through a longer wire. And then the area, that's kind of that lanes of the highway. If I make the thing wider, there's more room, there's more free electrons in there to move. And so you get a lower resistance because there's just more free electrons and more space for them to move around as well. And then resistivity, as I mentioned before, the higher resistivity, the harder it is to push it through that material. And that's just based on the material itself. So resistance is purely dependent upon geometric and material properties. Just like capacitance was purely dependent upon geometric and material properties. These are things that if I have a resistor, I can throw it across the room and it's the same resistance value. If I have a capacitor, throw it across the room, same capacitor value. Assuming I didn't damage it. So pretty straightforward there. The derivation here is coming from Maxwell's equation. I put it here, but I'm not really going to talk about it because we don't talk about Maxwell's equations in this class. But if you want it, it's there. You can do that on your own time. So now we get to do a nice, wonderful ratio problem. So I'll put the equation here. So length over area. So the question is, if I double the length and halve the diameter of a copper wire, what's going to be the value of its new resistance? And just its original resistance was R0. So it's going to be some ratio with that. And I'll tell you, this is a circular wire. Pretty much all these wires you can assume are circles. Oop, nope, it needs to go that way. There we go. Beautiful wire. Double the length, half the diameter. Notice there's no diameter in this equation, so you have to figure out how one of these variables depends upon diameter. And the cross-sectional area is this, just giving you all the hints. Give you all even Alright, gonna give you all about 5-10 more seconds. Still missing about 20 people. Alright, so 5, 4, 3, 2, 1. Okay. So, as I mentioned, you all, we need to figure out this ratio problem. So we don't know how the area changes yet because I didn't tell you explicitly. So how does area 1 relate to area 2? Well, area 1 is going to be pi r squared. Area 2 is going to be pi r2 squared, which will be pi r1 over 2 squared. If the diameter is half, the radius is going to get halved. So a2 equals 1 over 4 a1. So when you plug that in here, so R2 is going to equal rho 2 times L1, 1 over 4 A1, yep, that's fine, A1, which equals 8 times rho L1 over A1, R2 equals 8 times R1, R0. Be very careful when you're doing these problems to make certain that don't just look at the values that are there and immediately assume that they're the ones there. You got write down the math. Make certain it makes sense. Make certain it lines up. Sometimes doing things in your head, you can just make some simple mistakes, such as thinking that they're going that way. All right, I'm going to cover a couple last things. I'm not going to do. That's the same thing. Oh no, that's all right. There you go. Whatever, do this real quick. I'll give you all 1 minute, and then I have some final thoughts I want to give you. If I double the length and half the radius, one of the values to resistance. Hopefully this is a give me. Should be real quick. Last one, I have the diameter. Now I have the radius. So I'm going to give you all of up to maximum 1 minute to do this. And then there's a couple points I want to convey to you all before we finish. Alright. Gonna close it out in 5, 4, 3, 2, 1. Okay. The answer is the same thing. There you go. If you made the mistake, it's literally the same problem, so just double check that. Alright, I have a couple more points I want to mention to you all. This is more practical stuff. It doesn't actually have to do it. I'm not going to test you on this, but for engineers, good for you to know. Interesting to know. Alright, this is how you actually read a resistor. You have to do this in the lab, so make certain that this is useful review for that. You read it by reading, whatever, I'm not going to spend the time, I don't know what's paying attention for that. What I will spend time on is this one. I'll talk about that next time because not enough people paying attention, that's important. The material you choose matters. Alright, if you're leaving, please settle down and be quiet when you're leaving. We still have a minute left in class. I know you all have places to be. But if you want to talk, you're welcome to do so outside the class. The part we didn't talk about here is why you would choose. Why not just choose the one with the highest or the lowest that doesn't react with other materials? Gold is something that will stay gold, it doesn't oxidize. And so that's something you may not think about, but not only is cost a factor, but the environment it's going to be in. If you put in iron, while it may be cheap, it's going to oxidize. If it oxidizes, it lowers its resistivity, it's no longer useful, it'll break your device. So there's a bunch of factors you have to consider when actually using these in engineering application outside of just this has the highest resistivity or the lowest resistivity. So I just wanted to kind of cover that because while it's not, I'm not going to assess you on that. You're engineering, you're going to need to know these kind of things, and the real world applications are far more than just one value. All right, you're good to go.